Last time we defined exterior derivative, değil mi? Bir tane lambda diyelim ki bir tane one form. Bir lokal koordinatla şöyle yazılsın. One form. Its exterior derivative is just df wedge dz plus dg wedge dz bar. What is df? Df is just f sub z dz plus f sub z bar dz bar. So what we mean by this f sub z, just actually del f del z isterseniz öyle yazayım da. Del f del z del f del z bar dz plus dg del g del z dz del g del z bar dz bar which dz bar. Here dz times dz is 0, so we have only this product term. So del f del z bar dz bar dz plus here these two will cancel, so I have only this term del g del z dz dz bar. And we know that when you interchange two differential one form, you get a minus sign, so this is just del g del z minus del f del z bar, and then you have dz bar. This is in z bar coordinates. If you work in so we are in the Cartesian plane or C. If you use the coordinates z and z bar, this is what the differential and its exterior derivative. If you work with Cartesian coordinates, so then you have, let's say, fxy, the x plus gxy dy, then d lambda becomes just so df wedge dx plus dg wedge dy. Df is just del f del x dx plus del f del y dy wedge dx, and then this is just del g del x dx plus del g del y dy. And if you open these up and so here this will be 0, dx wedge dx. Here I have also dy wedge dy is 0, so the only non-zero terms will be this guy and this one. So I will have del g del x minus del f del y, and then dx wedge dy. Okay. Well, why do we use this notation? It's because of the following. We have so-called theorem, Stokes theorem for differential forms. So let's omega in C be a bounded region. Bounded region with boundary being a piecewise smooth curve, then integral of omega over this region is the same as, sorry, neyse tamam. Boundary omega is just for any smooth one form omega. Bu bildiğimiz Stokes teoremi. Neden? Yani oturup yazarsanız proof omega, şimdi diyelim ki fxy dx plus gxy dy d omega we just computed, it is just gx minus f sub y, right? Derivative of g with respect to x, and then minus derivative of f with respect to y, and then we have dx dy. How do we define these integrals? Well, you know, over a region like this, suppose, you know, our region is something like this, you know, this is our omega and this is the boundary of omega. Over this two-dimensional object, what is the integral of this? So the omega yani differential formun integrali nedir? Bunu tanımlamamız lazım. Tanımı da şu. Differential formun integrali, burada tabii düzlemin bir yönlendirmesini alıyoruz. Şu değişkenlerin sıralaması düzlemin yönlendirmesini veriyor. Ne demek bu? Bu birinci koordinatım, bu ikinci koordinatım. Yani şöyle x, y. So this is the, you know, this order should be compatible with the orientation of the plane. For us, the positive orientation is this. Okay, counterclockwise orientation. So first coordinate and then second coordinate should be like this. And in this case, this is just the, you know, usual Riemannian integral of this function over this region. Okay. Yani tanım bu. So that's the definition. Okay. Integral of a two form is defined like this. You have to write your form so that, you know, you should have dx dy, not dy dx. In that case, it will be just negative of that, okay? So that's the definition. But, you know, from the advanced calculus course, we know that the second integral, right? This integral is just equal to what? It is just the line integral f dx plus g dy, right? This is the usual Stokes theorem. And what is this? This is just, of course, the integral of omega over this, you know, curve, oriented curve. Of course, you know, that orientation of the plane orients also the, so here my orientation is like this. So this is my, you know, first vector. This is my second vector. That's the counterclockwise orientation. And this boundary of this region is oriented this, you know, accordingly. So here we have counterclockwise orientation. So when you compute this integral, you have to parameterize it so that, you know, you go counterclockwise. So these differential forms are introduced, one reason that they are introduced is that, this Stokes theorem becomes something really nice, right? So this thing is just this. So this is the Stokes theorem. This analytic object, which involves derivatives and so on, becomes just a geometric operator taking boundary, okay? So that's the power of Stokes theorem. It combines topology or geometry topology with analysis, okay? These two integrals are the same. Of course, if you just define things coherently. Okay, we have I am not sure if I had defined closed form, exact form. Tarif ettik mi? Etmedik, değil mi? A differential form is called closed if its exterior derivative is 0. So closed means its exterior derivative is 0. It is called exact if this omega is d nu for some form nu. Yani bir form close türevi sıfırsa ona close diyoruz. Eğer bu form başka bir şeyin türevi ise ona da exact diyoruz. Tabii ki şu var. Proof fact şu. If you have a form, then d squared is just 0 for any form. Yani bir şeyin 2 kere türevini alırsanız 0 olur. Bu fonksiyonlarda tabii ki doğru değil. Ama differential formlarda böyle. Geometrik olarak da öyle. Neden? So this is true for forms, but not for functions. I mean, of course, functions are 0 form, so it is true for functions, but what I mean is, if you take derivative of a function twice, of course, it doesn't have to be 0. But if you consider it as a 0 form, and if you take exterior derivative twice, then you get 0. Geometrically, this corresponds to following. If you just take boundary of a region, you get empty set, right? You have some object like this. Its boundary is this, right? What is the boundary of this object? Boundary of this, it is empty set. So the geometric counterpart of this fact is this. Okay? Now, I will not prove this in full generality. I will just prove it for 0 forms and 1 forms because we are dealing with surfaces, so we have only 2 dimensions. Okay? But in general, it's not difficult either. So proof. Let's take this gadget as 0 form. 0 form. 0 form means just a function. So what is the derivative of this? Exterior derivative. It is just f prime. Of course, I'm working in 2 dimensions, so it should be a function of x and y. So this is just f sub x dx plus f sub y dy. And if you take derivative one more time, so d squared omega is, so d of this. So what is this? So derivative of this, exterior derivative, you have to take differential of this and multiply with dx, and then take the differential of this function and then multiply with dy. Differential of dx is what? It is just, you have to take derivative of this gadget with respect to x, or f sub xx dx, plus derivative of this with respect to y, f sub xy dy, which dx, plus derivative, exterior derivative of this. So you first take derivative with respect to x, and then derivative with respect to y, and then you have dy here. So what is this? This is just dx, dx is just 0. So I have fxy dy wedge dx, plus dy, dy is 0. So only term that survives is this, dx, dy. And if you look at these, I can just switch this, and that will just pick up a minus sign, dx dy plus fyx dx wedge dy. But if it's a smooth function, and for a smooth function, it doesn't matter in which order you take the derivative. So f sub xy is the same as f sub yx, and you have a minus sign here. So this gives me 0, right? Because you have the same thing with two different signs, and you add them up, so you get 0. So what we see is that for a 0 form, this is 0. What about the 1 form? If you have a 1 form, so 1 form, omega is just, let's say, fxy dx plus gxy dy. We computed the derivative of this already. It was just g sub x minus f sub y, and then dx dy. Now, what is the second derivative of this? So you take derivative one more time. So you have this coefficient function. You have to take exterior derivative of this and then multiply with this guy. So exterior derivative of this gadget, times dx dy. But what is the exterior derivative of this? Let me just call this function h. Okay, so it is just h sub x dx plus h sub y dy, and then dx dy. But when you open this up, you get dx wedge dx. So that will give me 0. And here you have dy wedge dy when you open this up. So you have dx or dx in the first term and dy wedge dy in the second term. So let me just write plus so when you have two terms like this, you have automatically 0. Bu şeye benziyor. Yani bu wedge'in şeyi yani isterseniz onu şöyle söyleyeyim, remark olarak linear algebra'dan ve bir tane vector space olsun. Vector space. Şu da basis olsun. Bu da dual basis olsun. Bunlar vektörler. Yani bizim del xi'larımız. Bunlar da dxi'lar. Öyle görebilirsiniz. Yani bunu del xi at p ei star da dxi at p. So this is a tangent vector, this is a cotangent vector. Öyle görebilirsiniz. Bir tane form almak, differential ya da differential değil, form almak şey anlamına gelecek. Yani diyelim ki şöyle diyeyim, W1, W K burada nesneler olsun. Bu nesnenin vecinin V1 VK'da şurada vektörler olsun. V1 VK. Burada K tane kovektör var. Burada da K tane vektör var. Bu kovektörler bu vektörleri nasıl yiyecek? Değil mi? Bunların her birisi dual vektör olduğu için vektör yemeyi biliyorlar ama böyle yazdığınız zaman nasıl yiyecekler? Bu linear algebra fact. Bu şu matrisin determinantı. Hangi matrisin? İsterseniz şöyle yazayım. Determinant of, so this is determinant of Wi Vj'yi yiyecek. So the first row is W1 eats all these K vectors, and then W2 eats all these vectors, and you just take the determinant of this gadget, okay? So that's the definition. And here you see that if two of these are the same, suppose these are the same, then it means when you are taking this determinant, you know, this matrix has two equivalent rows, right? Two rows are the same. And in that case, of course, determinant is just zero. Okay? So this is the linear algebra behind this gadget. Tamam mı? Peki. Yani aslında this shows what? You know, this thing is just the determinant, and determinant is basically volume, right? Oriented volume. So this gadget is just measuring the volume of the parallel pipette formed by this vectors. So you have this K vectors, first vector, and then the second vector, third vector, and so on. And then you form this, you know, gadget like this, whatever, you know, tam olmadı. Neyse. Şöyle. Yok. Whatever. Beceremedim. Okay. Şöyle. Okay. So you are just computing, you know, volume of this gadget, but of course these things doesn't have to be just E1, E2, En. So it's a scalar multiple of the volume. Okay. O yüzden de hani işte integral diye tarif ediyoruz. Değil mi bunu integral? Çünkü bu bir volume hesabı. İntegralde de işte volume hesaplıyorsunuz temelde. Şimdi bu teoremin bir sonucu olarak corollary. Pardon. Bunu da çevirmedik o zaman. Değil mi? Şunu bir hatırlatayım. One form aldığımızda one form'un exterior derivatifini bu şekilde hesaplıyoruz. Burada da we have dx and dy and they are zero. And this is the linear algebra fact behind that reason. If you have a vector space and dual space, here you may consider EIs as, for example, tangent vectors at a point P, and these are cotangent vectors. And if you pick K vectors and K covectors, then you form this form, and form evaluated on this K vectors is just defined to be the determinant of the matrix whose ijth entry is Wi evaluated at the jth vector. And here this explains, if two forms are the same, then you get two rows of this matrix will be the same, therefore determinant is zero. And similarly, if two vectors here are the same, then two columns will be the same, and again it's zero. Okay, so now we have a corollary. Okay, if lambda is a differentiable one form on a compact Riemann surface, C, then its exterior derivative is the two form. Therefore, I can just compute over this surface, and this is just zero. So here we have this, we have a compact Riemann surface, C, and I have a differentiable one form on this. And here we take its integral. So how do we take integral over such a surface? This is done as in advanced calculus. You just parameterize your surface. Of course, you may not choose a global parameterization. Around each point, you choose a parameterization and so on. You just, compute it on parts and then add them up. And the proof is easy. This integral by the Stokes theorem is this. But, this is a compact Riemann surface. It has no boundary. This is just the empty set. So you have integral over the empty set, and integral over the empty set is defined to be zero. Okay. Peki. Şimdi Poincare-Hopf teorem. So this is the section 6 in the book. The Poincare of formula. Okay. Now let's see be a compact Riemann surface. Riemann surface. Then we have seen that for any meromorphic function f on the surface, the sum of the its multiplicity'leri mi diyorduk? Neydi bu? Order'ları mı? Yok. Order. Neyse bunun sıfır olduğunu biliyorduk. Buradaki şey de neydi? Aslında yani işte pol mu zero mu işin değil mi ona geliyor. Zero ve polların sayısının da aynı olduğunu biliyoruz. Ama pollar artı bir yani işte pardon zerolar artı pollar eksi sayılıyor. İkisi de aynı olduğu için sıfır geliyor. Bunu biliyoruz. Peki Poincaré-Hopf teoremi ne diyor? Poincaré-Hopf teoremi de şunu söylüyor. What about uh, what about uh, for a meromorphic one form omega. Yani bir tane one formumuz varsa o zaman ne olur? Şimdi teoremi indeksi tarif edeceğim. Şimdi teoremi state etmeden önce de before we state the theorem, I need to define several things because the statement involves stuff we haven't seen so far. But first, we have a definition. Suppose f from the circle into R2 minus 0. So you delete the origin from the plane and take a map from circle into the deleted plane. And suppose this is a smooth mapping. Then its winding number is defined to be the integral one over 2 pi times integral over the circle of f star pullback'i de tabii söylemedik. Neyse onu da söyleyeceğiz. Bunları açıklayacağım. D of argument of f. D of argument. Şöyle yani D of argument of F. Tamam. Şimdi nedir o? Nereden çıktı bütün bunlar? Efendim? Gauss'un, evet. Şimdi let's explain this formula. Uh, explain explanation. Şimdi closed formlardan bahsetmiştik ya. Closed ve exact formlardan. R2 minus 0'yu düşünürseniz burada bir tane closed form var. Aslında geri kalan bütün formlar o formun şeyi katı, başka bir şey değil. O closed formda şu, ona e, omega diyeyim mi? Dur bakayım. Yok, omega demeyelim. Ona d theta diyeceğim. Tamam, buldum. D theta. D theta da şu. D of theta is this gadget. So when you have a point here, so it is not at the origin. Theta is this angle. So what is d theta? Well, tangent theta is just y over x, right? Tangent x, y over x. So theta is just tangent inverse y over x. So this is tangent inverse y over x. Y over x. Değil mi? Söylediğimizde yazdığımız aynı olsun. So how would you take differential of this? Well, you take x derivative of this. And then dx plus y derivative of this dy. What is the x derivative of this? Okay, tanjantın türevi nedir? 1 bölü 1 artı içinde her ne varsa, değil mi? Çarpı içinin türevi. İçinin türevi de nedir? Y bölü x'in x'e göre türevini alıyorum. Eksi y bölü x kare dx plus y derivative of this 1 plus y over x squared. Y'ye göre türevini aldığım zaman da sadece 1 bölü x dy. If you clear the determinants and so on, so you will get x squared plus y squared here. And then, so you will multiply this by x squared. So you will have minus y dx. And here you will multiply by x squared. So you will have x dy. So you have x dy minus y dx. Okay. Is this form exact? It is derivative of something, right? So is it exact? No, it is not. The reason is that it is derivative of something, but this gadget theta is not a function on R2 minus 0. So remark is this. This theta, which is tangent inverse y over x, is not a function on R2 minus 0, 0. Right? Bu it is not defined on the y-axis. Therefore, this is not a exact form. Yani exact formsa bile bu exact olduğunu göstermiyor. Diyebilirsiniz ki belki başka bir şeyin türevi, değil mi? Bunun türevi değil. Çünkü bu fonksiyon değil. Burada şeyde dikkat edin. Yani bu nesne R2 eksi şeyde burada bir fonksiyon değil ama türevini aldığınızda fonksiyona dönüşüyor. Değil mi? O da ilginç. Şimdi evet, şöyle yapalım. Tamam, bir 10 dakikam daha var. Yok. Şöyle. Bu gerçekten exact değil. Ee, exercise olarak şunu bırakayım. Exercise. Bu d theta, which is x dy minus, pardon, yok. X dy minus y dx, x squared plus y squared. So this is the one form. We write like this. Nerede one form? R2 minus 0, 0. Right? This is defined everywhere except the origin. At the origin, it is not defined, but it is defined everywhere. Is closed. Yani ne göstermenizi istiyorum? Bunun bir daha türevini alırsanız 0. Tamam mı? Yani şunu. D of d theta is 0. Bunu şöyle yazamazsınız. Hani bu d square theta değil. Tamam mı? Aslında öyle de düşünülebilir. Neden? Çünkü türev almak yerel bir şey. Bu nesne de yerel olarak exact. Çünkü yerel olarak bir şeyin türevi. Ama yani doğrudan tanımı uygulayın. Türevleri ala ala bunun 0 olduğunu gösterin. But it is not exact. Neden exact değil? Onu ispat edelim. Let omega be, pardon. Okay, let's compute the integral S1 omega. S1 is just the circle of radius. Hatta hangi radius olduğu da önemli değil. Radius'ı R alayım. Let's parameterize this. So x is just R times cosine t. Y is R times sine t. T is between 0 and 2 pi. Okay. So what is dx then? Dx, here R is a constant. My variable is just t, okay? So when you take differential of this, dr cos t, this is just, R is a constant, so it just goes out, d of cosine t. Differential of cosine t, well, it is just, you take derivative of cosine, which is minus sine t dt. And what is dy? D of r sine t. What is the differential of this? R again constant goes out. Differential of sine t. Well, it is just derivative of sine. Derivative of sine, which is just cosine t dt. All right, so okay. Okay, let me just do the computation over here. Okay, so what is then d theta on this parameterization? X dy minus y dx divided by x squared plus y squared. So x is just r cos t. Dy is just dy r cos t dt minus y r sin t, and then dx is just minus r sin t dt divided by x squared plus y squared. So r cos t squared plus r sin t squared. So when you open this up, you get r squared cosine squared plus r squared sine squared. So it is just r squared cosine squared t plus sine squared t dt divided by the same thing, r squared cosine squared t plus sine squared t. Well, this is just dt. So this integral is then integral over S1 of omega. This is parameterized as just the curve from 0 to 2 pi. And omega in this parameterization became just dt. So this integral is just 2 pi. In particular, what is the winding number? Winding number. So the winding number of F. Yani çemberi, bu birim çember S1 R'a götürsün. Nedir yani bu fonksiyon? F x y birim çemberi yarıçapı R olan çembere götürüyorsunuz. Yani ne olur bu? Rx Ry değil mi? Rx Ry is equal 1 over 2 pi times S1 F star u dy minus y, no, v du divided by u squared plus v squared. Okay, just this integral. And we have seen that this thing, şu f star'la bunu geri çekme işi dediğimiz şey şu işte. Yani bu uv yerine ben xy yazdım. Bunu bu fonksiyonla geri çekiyoruz. Yani f x y rx ry ile geri çekiyoruz. Yani işte şunu parametrize ettim. Sonra da onu t cinsinden yazdık. Bu integralde işte 2 pi çıktı. 1 over 2 pi times 2 pi. So it is 1. So the winding number of this circle of radius r is 1. Bunda da ne demek? So if I choose a circle of radius r, the winding number of this is 1. Neyin etrafında dönüyor winding number? Orijinin etrafında. Burada dikkat ederseniz hani bu form nerede anlamlı? Yani R2 eksi işte orijin değil mi? Şöyle. Pardon. Bu formun yaptığı şey tam olarak verilen bir eğriyi integre ettiğinizde o eğri orijinin etrafından kaç kere geçiyor onu buluyor. Genelde de okey. Bir dahaki ders devam ederim. Let me stop here.